Since the dawn of civilization, humanity has gazed at the cosmos, pondering how the universe began and whether it will ever end. Two of the most significant theories to emerge in our quest to understand the origin and evolution of the universe are the Big Bang theory and the steady-state theory. Both sought to answer the same foundational questions, but their answers differ profoundly. Exploring their history, evidence, and implications leads us through some of the grand debates of 20th century science and casts light on how humans progress in the search for cosmic truth. Imagine standing under a starlit sky, seeing billions of points of light scattered across a limitless darkness. For centuries, people thought the universe had always been as it was, eternal, unchanging. This idea of a static universe held sway until the early 20th century, when advances in astronomy and physics began to challenge the ancient view. But this challenge would not go uncontested. The steady-state theory and its revolutionary rival, the Big Bang theory, would soon go head-to-head on one of science's greatest stages. Let's begin with the steady-state theory. In 1948, scientists Hermann Bondi, Thomas Gold, and Fred Hoyle proposed a radical idea. They suggested that although the universe is expanding, as had been observed by Edwin Hubble, the universe has no beginning or end in time. It simply exists as it always did. As the universe expands, new matter is continuously created, so the overall density of the universe remains constant over time. In this model, the universe looks more or less the same no matter when or where you observe it, an idea called the perfect cosmological principle. The steady-state theory was elegant in its own way. It sidestepped uncomfortable questions about what happened before the universe began and what might happen in the infinitely distant future. It preserved a kind of cosmic equilibrium, avoiding the messy implications of a cosmic genesis. Yet, even as the steady-state theory was taking shape, another idea was gaining traction: the notion that the universe had a beginning. This concept was rooted in an interpretation of Albert Einstein's general theory of relativity. Georges Lemaitre, a Belgian physicist and priest, first proposed in the 1920s that the universe had originated from a single, incredibly dense point, a primeval atom. This concept was later developed most prominently into what is now known as the Big Bang theory. The Big Bang theory stated that all the matter, energy, space, and even time itself began in a single, infinitely hot and dense state, and has been expanding ever since. In this view, the universe has a history, a dramatic point of origin some 13.8 billion years ago, followed by rapid change, cooling, the formation of atoms, stars, galaxies, and eventually the universe we inhabit today. Evidence was mounting on both sides. Hubble's discovery in the 1920s that galaxies are moving away from us, redshifted in all directions, suggested the universe is expanding. Both the steady-state and Big Bang theories could accommodate this, but made very different predictions about the universe's history and fate. For the steady-state theory, the expansion of the universe meant that new matter had to be generated continually to maintain a uniform density. This process, though never observed directly, was central to the theory's viability. On the other hand, the Big Bang theory predicted that, as the universe expanded, it cooled, leading to a series of physical processes that gave rise to the matter and structure we see today. The true test came with observational evidence, data that could distinguish between a universe with a beginning and one without. One of the key predictions of the Big Bang is the existence of residual heat, what is termed the cosmic microwave background radiation. If the universe was hotter and denser in the past, then, as it expanded, leftover radiation from that hot phase should permeate the universe. In 1965, while working on experiments unrelated to cosmology, Arno Penzias and Robert Wilson stumbled upon this faint background glow. No matter where they pointed their radio antenna, a persistent, low-level hiss could be detected, the perfect match for the afterglow of the Big Bang. This accidental discovery was a monumental moment. The steady-state theory had no way to account for this all-encompassing radiation, whereas it was an explicit prediction of the Big Bang model. For many, this was the deciding blow. Further support came from the observed abundance of light elements such as hydrogen, helium, and lithium in the universe, which matched calculations based on the conditions of a young, hot universe just minutes after the Big Bang. The steady-state theory did not have a mechanism to explain these abundances. As more and more evidence accumulated, the Big Bang theory became the dominant framework in cosmology. Yet, it is instructive to examine the steady-state theory not as a scientific misstep, but as a vital part of how science operates. The steady-state theory challenged astronomers to look for observations that could distinguish between a universe with a beginning and one with none. It inspired experiments, guided observations, and sharpened the questions scientists asked. In this sense, the clash between the Big Bang and steady-state theories was a necessary stage in the progression toward scientific truth. Despite its apparent defeat in the face of the microwave background radiation, proponents of the steady-state theory tried to adapt their model. Variations such as the quasi-steady-state model were proposed, suggesting cycles of expansion and contraction layered atop an overall steady-state background, but none provided a better match to the accumulating mountain of evidence for the Big Bang. Still, the Big Bang theory is not without its own mysteries and unanswered questions. For one, what caused the Big Bang? What existed before time and space themselves sprang into being? These are questions at the very edge of human understanding, bordering on the philosophical and metaphysical. To address some of the finer points, scientists refined the Big Bang model, developing concepts like inflation, a sudden burst of expansion in the earliest moments of the universe, to explain the uniformity and structure we see today. Yet, even these ideas open new questions about the true origins and ultimate fate of the cosmos. One of the philosophical implications of the Big Bang compared to the steady-state theory is their relationship to the concept of eternity. For much of human history, the idea of an eternal universe was comforting and even logical. Having a universe with a beginning, however, hints that the universe might also have an end. A heat death, perhaps, where all stars burn out, the cosmos grows cold and dark, and time drifts into an endless silence. The steady-state model, with its never-ending, ever-renewing cosmos, avoided this specter, holding out the promise of eternal existence. Religious and cultural interpretations also intersect with these scientific models. For those inclined toward religious explanations, the Big Bang's beginning resonates with creation myths, an echo of the moment when the heavens and the earth were made. For others, science's sprint toward a comprehensible, natural cause behind the universe's emergence is a profound testament to human curiosity and intellect. Today, the steady-state theory is largely considered a historical curiosity, an important part of the transition from old, static models of the universe to the dynamic, ever-evolving universe revealed by the Big Bang model. Yet its philosophical undercurrents, and its role as an intellectual challenge to cosmologists, remain influential. The process by which it was tested, examined, and eventually set aside is a model of scientific progress. Ideas are born, battle for dominance, and are settled by the weight of evidence. The Big Bang theory, meanwhile, continues to guide research and exploration. Astronomers today use sophisticated telescopes to look farther into space, and thus further back in time, searching for the earliest galaxies and the subtle fingerprints of the cosmos's first moments. Scientists debate the meaning of dark matter and dark energy, those mysterious substances and forces that shape the universe's destiny. Each discovery opens new puzzles, continues to shape our understanding, and adds to the tapestry begun by thinkers who dared to imagine a beginning and an ever-changing universe. In the end, the story of the Big Bang theory and the steady-state theory is not just about which is correct. It is the story of human imagination and perseverance, and our willingness to challenge the status quo, propose bold ideas, and test them against the unforgiving standard of nature herself. While the Big Bang theory now reigns, it too will continue to evolve, refined by new evidence and tested by new minds. The ultimate journey to understand our origins is far from over. So, as the stars wheel overhead and cosmic background radiation whispers of a fiery birth, one truth remains clear. The universe is more dynamic, surprising, and wondrous than any one theory alone could ever describe. And the human drive to know, to seek, to question, this too shows no sign of reaching a steady state.